Okay, welcome to Wednesday. I'm not going to record very much on this one because I don't think I need to. Recordings will now be quite selective. If any of you do miss sessions, then the chances are the materials are already on YouTube. There's a huge amount on there. It's just, I do need to go through all the files that I've got on there and make the titles a bit more searchable. What I did before was to get people, or to keep it all private and to give people a login for it, because I used a login which was my old Lowestoft College email address, so it was l.leuty@lowestoft.ac.uk, and the password was access 2017, and so people could just log on as me and get to the stuff. And it didn't access any other of my materials, obviously, and it was just, quite useful like that. The problem I had then was that every time somebody logged on from their phone or laptop or whatever, I would get a notification, oh, there's been unusual activity, somebody's logged into your whatever. And actually, over the last 2 years, the security on it has actually got a lot tighter. And if I did that, if I can give you that to log in, but I suspect there will be various problems, and you'd end up having to get codes to put in, and it would have to come to my phone. And so, the only other way to make it more accessible would actually be to set people up as subscribers, I think, to have a list, to put your emails in, your personal emails, so that you could then access it. So we'd have like a sort of private group, I think. I'm not that experienced with it, I haven't done that yet, but it's just easier at the moment to leave them public, but to make them easily identifiable. And I'm going for putting my name on the beginning of the file names, because there's not many people with my name out there, so that should make them searchable. Um, if you type my name in, you should find them. Yeah, but I want to try and go through and make all the titles of them fairly obvious. Some of them are really obvious. I did get into a very good habit in I think the final chemistry unit. I literally just called it Energetics 1, Energetics 2, Energetics 3, and then Redox 1, Redox 2, Redox. It was really, really clear on that. And I think I did the same with the final biology unit as well. But a lot of the early stuff that I did 2 years ago has got very vague sort of titles. So if I show you, it comes up, for me, I get a list like this. So they don't have my name on, but there's a couple there on the kidney structure, and then some of the other stuff. Hess's law calculations are to do with the chemistry. Actually, I think that's page 2. But I've just gone through, no, it's page 3, isn't it? No, page 1 is what we're currently doing, isn't it? Page 1 is the newest ones. Hang on, if I go to page 3, I could see some on there, actually. Organic mechanisms. I mean, that's what we did Monday. Example organic mechanisms is on there as well, but it doesn't have my name on it, so it's vague. Immune system, although I can see on that immune system one, it's not just the immune system, because that's got a oxyhemoglobin dissociation curve on it as well. I've just started today going through, and the things that we're doing at the moment, I've attached my name to. So I have attached my name onto heart structure and cardiac cycle. So that's that one there, second up from the bottom. Blood vessel structure, just above that, which we're doing this morning, and heart control, which we're doing this morning. So it gives us an idea of sort of how much work we've got to do this morning. But I'm going to go through and sort of tidy them up a bit like that. There are some that I'll re-record, which lost sound you might see on there sometimes. Loses sound part way through, or no sound, because, these things are a bit temperamental. But I will go through all that, and I'll try and get it organised. But it takes a little while to do, so if you're in contact with anybody who's missing any of the sessions, then you can tell them that there's plenty of material out there, and I'm recording this so that I can post it with instructions anyway. So what we did on yesterday, it was yesterday, wasn't it? oh, feels like a long time ago. Um, yeah, so we went through a rather strange diagram of the heart, sort of building up the structural components of it. The left side being on the right side of the diagram, the right side being on the left side of the diagram. The right side of the heart over here, dealing with deoxygenated blood, hence the blue labels, atrium, ventricle, valves, blood vessels. And then the left side of the heart over on the right side of the diagram, dealing with oxygenated blood again, atrium, ventricle, 2 valves, 2 blood vessels. A few key points about the heart. The fact that the muscle is myogenic, it generates its own contraction. Left side's thicker than the right because it's got to pump to the body. And we have the coronary circulation to provide the heart muscle with its own blood supply. We also looked at the cardiac cycle, systole and diastole. The systole bit, I then had an arrow coming around to show that it's got 2 components. The contraction of the heart is the atria followed by the ventricles. And so down here we have the conduction system to explain that. But the equally important is the diastole, the relaxation or the filling part of it. That just all happens at once. But the way that the heart contracts in sequence, atrium or atria, then ventricles, requires this conduction system, fibres that run through the heart, conducting a wave of depolarization. Okay, that's I have got the green label over there at the top right. This wave of depolarization is what the red arrows are showing. It all starts at the sinoatrial node, this little leaky area of tissue up here, leaks ions until it depolarizes. That then spreads through the atria, so they contract down, pushing the blood through the valves into the ventricles. The wave of depolarization shoots down the septum of the heart through the bundle of His, which is made of this Purkinje tissue. And then the contraction starts again, but from the bottom upwards, so it pushes the blood up. In doing so, and this is sort of where I now need to pick up, the valves back to the atria will close, but the valves out of the arteries will open. And we're going to start looking at how the valves open and close and the relationship with pressure changes, heart sounds, ECG tracers and all that sort of thing. But I have already got that recorded elsewhere, so I'm not going to continue the recording for that bit on here. The whole conduction system is potentially a source of disruption to the heartbeat. You can have things go wrong with that conduction system, so people can have problems with their heartbeat that might require things like a pacemaker. So if the depolarization isn't being conducted properly, let's say from the atria to the ventricles, you can put a pacemaker in that will actually wire in to the, I think, into the AV node and just send an impulse that will keep the ventricles contracting at a regular pace. I used to have a rather peculiar little shortcut in my conduction system, so that when the atria had contracted and the wave of depolarization had gone to the bottom and then come up to the top, up the ventricles, it would then immediately short circuit round and go off again, and it would cause an incredibly fast heartbeat. So my heart would go, I think my personal best was 235 beats a minute. And you can't count that, I only know that because I saw it on an ECG machine. And the problem with that is if it goes that fast, it doesn't have time to fill. And this is, when I said that the diastole is equally important as the systole, then, that's the problem. Your heart starts going so fast that it's just contracting. It's not actually getting any blood going into it. So your blood pressure drops to virtually nothing because nothing's being pumped out. And it was I had to go and have it burned out, the little accessory pathway that was looping it back round through the AV node. So I went to Papworth and they threaded electrodes through my heart and burned that bit out, and it doesn't do it anymore. I can feel it trying to sometimes, but doesn't cause me any problems now, which is good. Right, the next thing that we're going to do is to look at the graphs that you've got in your handouts and look at things like pressure changes and valves opening and closing and heart sounds and all that. And so I'm going to, well, actually I might as well continue. I will continue the recording on this occasion, but then once we move on to blood vessels, I'm going to leave it over to the ones I've already got on the system. All right, now in your handouts then you've got this sheet, all right, with the 4 little hearts down the left hand side and a rather scary looking graph combination on the right, and then on the other side of that sheet you've got that same sort of graph combination on one of those labelled diagrams that are used quite often to identify bits of charts. So what I'm going to do is to sort of break that down. I'm going to do sketch versions of those graphs. Oh yeah, I just did a snip of the files that are on YouTube at the moment in terms of yeah, helpful stuff for the current section. I will leave that on there for those who need it. And we'll have a look at these graphs. Now, there's all sorts of ways of monitoring cardiac activity. And so that reminds me, actually, I probably ought to use the PowerPoint first. Have you got the PowerPoint? You probably haven't. No, you wouldn't need. It's not terribly helpful because it's got animation in it, which doesn't work. Right. I think this will be on Moodle. I think I put the whole set of useful PowerPoints onto Moodle. Just bear with me. Circulatory, very organised. Heart. Okay, so you haven't got this, but this will just lead us in. I really ought to put the graphs onto the back end of this, really. Okay, so we've done the structural stuff then. We know left side of the heart, right side of the diagram, oxygenated blood. Right side of the heart is the left side of the diagram, deoxygenated blood. This flow of blood through the heart is controlled by the conduction system. And what we end up with, I mean, looking for animations on this can be very helpful. That's a very, very simple one, but it gives you an idea of, you know, the sequence. So it's top down, bottom up, top down, bottom up, top down, bottom up. Without the actual blood flow and looking at valves opening and closing, this one is quite useful. And I did these when I was just trying to find out whether you could copy and paste animations into a PowerPoint. Turns out you can. So, you know, if you're putting PowerPoints together and you want animations in there, you know, if you find the right sort, they will literally just copy and paste. If you start with the atria, right, atria filling, atria then contracting. As the atria fill, the valve through to the ventricles is open. So that's open. Then it closes as the ventricles contract. As the ventricles contract, these little valves open. And then when they've stopped contracting, they close again. So we've got valves opening and closing. Now, when you look at this, this gives us all sorts of ways of monitoring what happens in the heart. For one thing, you can just listen to it, can't you? Or you can feel it. You can take a pulse. All right, so you can take a pulse, you can listen with a stethoscope, you can use an ECG, you can use ultrasound, all sorts of things. I'm just going to go through some of the things that you can actually monitor. If you're going to try and follow the actual flow of the blood, you can then find animations like this one, which is a little bit harder to actually understand the shape of that diagram, and they talk about pulmonic veins and valves instead of pulmonary. Weird when they say pulmonary arteries, but it takes you through the sequence, sort of lighting them up as it goes as well. So you will find that on Moodle, I hope. Right, Now, if we look at how we can monitor this, and this is leading into the graphs, that's why I've sidetracked onto it. Pulse points are points where arteries, not veins, arteries come near the surface of the body, and they are against hard materials like bone or tendons and things like that. You cannot feel a pulse in a vein. There is no pulse in a vein. You only get pulses in arteries. We'll see why later on this morning when we get onto blood vessels. So these are all arteries. You have up the side of your head, you might occasionally be able to feel that. I'm not sure it's a good thing to be able to feel a pulse in your temporal artery up there. Carotid artery in the neck is the one that I find most easily accessible. You should be able to find one at the elbow, but I think you'd have to be professional to get that. Radial, the one at the wrist, just at the base of the thumb, should be easy, but I haven't got one that I can ever find there. And then there are others that you don't want to try and take on a casualty. Femoral at the groin. However, if somebody's badly damaged their leg, you might need to. Pedal in the foot and posterior tibial at the ankle. So there are all sorts of places where you might need to find a pulse to see if there's been any damage to blood vessels. But what a pulse is really just the stretching of the arteries and then their recoil. So as the blood is pumped into them, they stretch, and then as the heart rests, as it goes into diastole, the blood vessels, the arteries will relax, and you get the recoil between. So taking a pulse, those are your typical places. Using a stethoscope, proper name for it is auscultation, but we still say using a stethoscope. And when a doctor listens to your heart using a stethoscope, they move it about over different areas of the chest, either side of the sternum, the breastbone, and that's because they can hear the activity of the valves. The valves are these little flaps of tissue, so if they're leaking, that's something that can actually be picked up with a stethoscope. Blood pressure measured using a sphygmomanometer. And we've got some we've got a couple at the back, so you can have a go at your blood pressure later on this morning if you feel like it. Wait till you're really relaxed. Blood pressure works by inflating a cuff around your upper arm so that it cuts off the blood supply into your lower arm. So that's why it hurts. It is significant pressure. And then releasing that pressure until, either with a stethoscope or electronically, the blood can just get through. So you're then matching the pressure of the heart. So you get this high number, which is the pressure that the heart's exerting. And then you can hear a pulse, and then it gradually gets fainter and fainter until it disappears, and then you're left with just the remaining pressure in the blood vessels. So you get a systolic pressure is the high one. That's when the blood's just squirting through. And then the diastolic pressure is when it's then running smoothly. We can do ECGs, electrocardiograms. Now, they pick up the depolarization. So they are picking up electrical activity in the heart. They're not telling you when it's contracting and relaxing. They're actually picking up that depolarization. And they can be done from various points of view on the body. Sometimes you might just have 3 electrodes across the chest. Sometimes they're done shoulders, don't know where that is, thighs probably, wrists, ankles. You can have a full 12 lead ECG that goes in a sort of quarter around the chest on the left hand side, and wrists and ankles, and it's giving like a 3-dimensional view of the electrical activity of the heart. So in terms of sort of diagnostic features, then they'd be looking for different aspects of what happens in a heartbeat. Now, a standard ECG trace, and although you haven't got this PowerPoint, you have on the handouts got as part of the big graph on the second side there, blood flow through the heart. Part of that is an ECG trace, and it tells you what these different bits are. The first bit, the P wave here, is when you get the depolarization of the atria and they contract. The second bit, the big bit, which is the QRS complex, is when the ventricles contract. So that's the wave of depolarization through the ventricles. Now, at the same time, the atria relax, but you can't see that on there because it's swamped by the ventricles contracting. Then you get the T wave, which is when the ventricles relax, and then you get this little blip, the U in there, and I can't remember what that is because we never usually bother referring to it. But the distance between those waves, or the absence maybe of one of them, if the atria weren't contracting properly, you might not get a P wave, or it might be a very small one, or you might get several P waves before the ventricles contract. It's a condition called heart block, when it's not actually passing on the wave of depolarization properly. So you can get a lot of information about heart activity from an ECG trace. One of the weirdest things is I think I've got it coming up actually, if the QRS complex is upside down, it indicates a heart attack. This is a normal 12 lead ECG, and you look at that and think, I have no idea what that is. But 12 leads, that's the top 3 rows. And if you read across, if you read down, they go 1, 2, 3. And then if you go to the next section, we've got another section of 3, and then V1, V2, V3, V4, V5, V6. So you've actually got the 12 leads are in those top 3 lines, and then they're all put together to form the bottom trace. So the bottom trace is the overall ECG, and then these other sections are like little snapshots to show, what's actually happening from different parts of the heart, so you can identify if there's any damage anywhere. That's what I used to have, SVT, and you can see that it just goes ridiculously fast. And I have a lot of years, and glad to be rid of that. 2002, I had that sorted out. That's what happens in a heart attack. You get this upside down sort of trace, which I have no idea why, but obviously, it is a very, very useful thing to do. The problem with these, though, is very often when they do them, the snapshot that they take is only over a very short period of time, and it doesn't necessarily pick up problems. But you might have heard of people having 24-hour ones, where it's tracing, what's going on for long periods of time. You can use an echocardiogram, which is ultrasound, effectively. And you can see which way up is the heart on that. It's upside down, isn't it? Yeah, you can see the atria down at the bottom, the ventricles are at the top, and the valves, the atrioventricular valves, are in between there. But it's not a very detailed one. But you can also use a type of echocardiogram that is real time. And it uses something which you won't have come across in physics yet, and that's Doppler. Or have you? Have people heard of, what the Doppler effect is? Or heard of it? The Doppler effect is to do with waves changing in frequency as they come closer or further away. Like the effect of, the classic is a siren, isn't it? Coming towards you and then going away. As it comes towards you, the sound waves get compressed, so it seems to get higher. And then as it moves away from you, the sound waves get stretched out, so it seems to go lower. So moving objects, their speed and their direction can be tracked using the Doppler effect. And this is Doppler ultrasound, effectively. And what it does is to track blood flowing towards the ultrasound, what do you call it, transducer, I think, and away from it. So although we've got red and blue on here, which makes you think, oh, oxygenated and deoxygenated blood, it's not. It's actually flowing towards and away. And this would be used, and it says mitral valve on there. So it's actually looking for leakage through the mitral valve, probably. So it is just another form of ultrasound. Oh, it actually tells you over here, B is blue. Well, blue, A away, R red, T towards, So, yeah, I'm not sure where that relates to, but red is towards and blue is away, I read from that. Oh, it's actually, no, it's not the mitral valve, it's the aortic valve regurgitation. So the aortic valve is leaking, basically. We haven't really talked about what that does yet, but I'll come on to that in a minute. You can also use angiograms, which are X-rays, really. X-rays of blood vessels where a sort of contrast medium's been injected in, so that something that X-rays don't pass through is injected into the blood, and you can pick up, there's a little narrowing there, there's an actual blockage there, but it gives like a little map of blood vessels so that it's possible to see, you know, where blood vessels are constricted or blocked. That's probably, oh no, I've got one more just because I liked that one. That was just a really, really clear sort of idea of an angiogram. But this was just showing the aorta, really. You can see the coronary vessels in the heart behind there, but other than that, it was showing other vessels. So there's a lot of things that happen in a heartbeat, or happen during the cardiac cycle, that we can track. All right, we've got all sorts of things, hence this sheet that you've got. Now, I could try and use both sides at once. I think I'm tempted to sort of skim over the first side with a smaller graph, and I'm just sort of focusing on some of the ones on the second side because they are the same. On that sheet you've got, and I would perhaps almost be sort of tempted to divide it up. You've got 4 things being shown, I think. At the top, you've got an ECG trace. All right, so I'm just going to sketch this out with no real detail on it. All right, you've got your axes a bit like that. And over the top, you've got this bit. So you get P, Q, R, S, T, and so it goes on. And then it starts off again over there, right? So that's your ECG trace, and there are label boxes that tell you what's going on there. Over the left-hand side there, you've got the P wave indicates. All right, I'm not going to read it to you, you can do that. But this is showing the depolarization moving through the heart as it contracts and relaxes. You've got a label box up at the top for the QRS wave or complex, and then the T wave is labeled over on the right-hand side. Okay, so that's one set of information, and you could have that on a graph on its own. It's just that this is a combination of everything. Underneath that, you've then got pressure. Now, the pressure one is the one that I would like you to be a bit more interested in. I'm going to come back to that one, I think. No, I can't really. I've got to do that in order. But you've then got, underneath that, you've got volume, and then underneath that, you've got heart sounds. All right, let's have a look at pressure. There are 3 lines in the pressure bit, and it's just looking at the left side of the heart. Now, if we were to plot the right side of the heart, what would the lines be like? Lower, but otherwise exactly the same. Yes, spot on. The left side of the heart is thicker, it contracts more strongly because of having to deliver the blood around the body. So, and this does relate to an exam question, I think. I can't remember if it's, I think it's in the merit distinction section, or it might have been, I don't know whether it's still there. But the left side pressure is higher. The right side, you could draw exactly the same lines, but just lower down. All right, because it's not so thick, it's not contracting so strongly. So you have 3 lines there. Now, I'm not going to do all the detail on them, all right, because it'll get messy. What should we start with? You've got an atrium, a ventricle, and the aorta. Can you see those labelled just down the right-hand side against the lines down here? Arterial, brackets aortic pressure, left ventricular pressure, and left atrial pressure. if I draw the ventricular pressure is the big line. So this goes, ventricle sort of starts to fill up and then does a big pressure change. Right, so that's the ventricle, left ventricle. Now, what happens in the ventricle is the pressure in the ventricle starts to increase as blood just trickles into it from the atrium. So that's this little blip. But then there's a huge increase in pressure because what happens? It contracts, yeah. So this big rise in pressure there is the contraction of the ventricular wall, applying pressure to the blood. As that happens, it closes the, if we're on the left side of the heart, it will be the mitral valve, won't it, the bicuspid valve, which stops blood going back into the atrium. Now, that creates a sound in the heart. Now, if you listen to the heart, you hear a heartbeat as two sounds, don't you? So I'm now jumping to the bottom of the graph. They actually have names. The first sound is lub, and the second one is dup. Right? Seriously. Lub, dup, lub, dup, lub, dup is your heartbeat. Now, the lub sound is created when the ventricle starts to contract and the bicuspid and or tricuspid valves close. Now, it's not the valves closing that makes the sound. They don't slap together, right? But they're pushed together and the blood stops up against them. So it's like a vibration. It's like a shock wave that creates that sound. And the only thing I can describe it as being similar to, and you'd have to live in my house to appreciate it really, it's like if you've got slightly dodgy valves in your water supply, if you turn taps off really quickly sometimes you get a thump in the pipes, but we get it with our washing machine filling. When the washing machine fills, it reaches a point and then the valve closes in the machine, doesn't it? And we get quite a thump in the pipes when that happens. And that it's like the valve closing in the heart. It's not the actual valve shutting that you hear. It's a shake in the pipes, and it makes it rattle a bit. It makes it sound really awful. It's not that bad, but you get the idea of it. So the blood being stopped. So somewhere we must get the second sound. We'll come to that in a minute. So the heart contracts, the ventricles contract, we get this big rise in pressure. Where is the blood going? It goes out into the aorta, doesn't it? So if we now put the aorta on here, I'll put this in as a red line, its pressure was falling between beats, and then as the ventricle begins to contract, of course, it really just becomes an extension of the ventricle. So you can see that the pressure in the aorta is going to be pretty similar to the pressure in the heart as the ventricles contract. Why wouldn't it be? Ventricle contracts and pushes the blood out, so you've got the same pressure in the aorta. Then the ventricle starts to relax. Now at that point, the pressure is going to fall in the aorta. You're not pushing the blood out anymore, and the blood starts to try and fall back in. Now that causes the aortic valve to close, so it can't fall back into the heart, and that's what causes the dup sound. So if you line up the two heart sounds on the bottom of that diagram, you can see that they line up with, I haven't got that quite right, but it's, something like that. All right, so that's going back, whoops, get the general impression. All right, so the aorta, messy a little bit here, but where the valves are closing, we've got one closure here, that's the AV valve, bicuspid or tricuspid, and another close here, which is the aortic and or pulmonary valve. So those bits line up with the heart sounds down at the bottom. There's also a line trailing along the bottom here for the atrium, but we're never too fussed about that really. That gradually fills with blood. It does contract just at the beginning there. It's not really, that's one that we don't really ever bother asking you questions about. It's the aorta and the valves and the ventricle, or the vessel, the valves, and the ventricle. Oh, that's easy to remember then, isn't it? Yeah, which bits do you need to know on the pressure graph? Vessel, valves, ventricle. Ventricle, vessel, valves, doesn't matter which order, does it? Okay, the other things that you've got on there are reasonably obvious, I guess. You've got the third part of this, volume of the left ventricle. Well, the volume of it is going to be greatest when it's full and smallest as it contracts and empties. So as the ventricle fills, you'll get an increase, and then as it empties, it'll go down, and then it'll relax, it'll start filling up again, so you get that. And then the line you've got across the bottom there, you've got your heart sounds associated with the valves, so there they are, like that. So this is why, listening to the heart can tell you a lot about valve function. But the bit that is, important really is this middle section here. So that black line and that red line, those are the bits that we really we'll come back to them in revision anyway, because they are the most significant parts that you need to know. So there's quite a lot of information on that sheet. It takes you sort of through little explanations of a lot of bits that I've not explained on here, because you don't need all the detail, but it is just understanding how pressure changes will open and close valves, really, and relating the two things to each other in a ventricle and a connected blood vessel is the important bit of that. Okay, all right. So we've reached a sort of tidy point now on the heart, and so the next thing I'm going to do is to move on to blood vessels. So I'm going to stop the recording at this point, and anybody who needs it can go hunt it down from the last time I did it. So it is on YouTube already. So let's turn that one. But it is there.